Hello, welcome back. Okay, so we're doing a little R review session. Unfortunately, I had to change the timing, and I realized that most of you are not available to join at this time of the day. So that's why I'm recording it, and I put it out there for you to watch. This now online as a recorded version. So essentially what we're doing is we're going through the practice lab, and I will, based on this practice lab, explain a couple of things in R. I wish it could have been more interactive, but it was just timely not possible. Okay, so again, we have RStudio as our preferred compiler, and I hope all of you that are using Google Colab have had a chance to review the video that I've posted about Google Colab. And in essence, both are to some extent comparable in its functionality. The codes will be the same, and the possibilities essentially are quite limitless what you can do. So when we look now into our practice lab completed code, there's actually a typo in there. Okay, good. So now let's open the practice lab and let's have a look at what we actually want to accomplish. So I'm just walking one by one through this code now. It's opening up here. So as said, we have on the first two lines, we basically have the completed and the clearing command. So RM is really a removal code where you can either remove specific objects that you see here on the right listed. Or maybe let's start early. Okay, so you have here, always here on the left upper quadrant, you have the respective script. This script, you can use additional script, you can open new script, you can open previously saved scripts, and you can address each of these tabs individually up here. You have on the left lower button, you have the actual console, which essentially is the core piece, which is R. Terminal and jobs are basically not relevant for you at this point in time. Terminal is essentially the programming part of R, which is at this point not necessary to understand. Jobs is basically jobs that have been listed as jobs to be executed, and I will actually walk through those. So here we have now our practice lab code, which essentially has here the RM function. So RM is really a function that can remove whatever object you have in your environment. So you have here on the right top, you have the environment, here the respective objects that are contained in your environment. Here for me, it's 3 of them. You have here on the right lower button, you have files, plots, packages. Packages is something that we will be using down the road. You do in R a lot of package use. Packages are basically packages that had been programmed and published by R itself. And you have the so-called CRAN, which is basically the package repository. You can either download them from online, or you can download the packages from any website directly or from the CRAN directly, and then load them into R. But basically, starting to enter the package you want to start, you essentially you start typing the name of the package. It will automatically give you whatever is available under that name. So Dubai, for example, is a great package that I use quite a bit. So we're gonna select Dubai, then we click on install, and it will automatically establish access to the CRAN, download that package, and automatically install that package. You see here when you install it from the packages tab here in RStudio, will automatically use the command install packages, which essentially is the command that you would use to start a package. If you have the package installed and you want to actually address it, you would do library as a command that basically opens your package and then enter the name of the installed package, and it will then start that package in your environment. When you close R, it will essentially stop using that package and you will need to address it again with library. Good. So RM removes now whatever you want to remove. So if you go on RM ANOVA test, for example, as an object in my environment, you can just remove ANOVA test. Good. So now it's gone. List is a command that basically tells RM, okay, so there's a list of things following now. I could hypothetically do a list equals C for concatenate, df, comma, enhance. That would basically a list which removes them. These two packages seems to be different to be used. Comma. Okay, doesn't matter now. It basically it will ask for a list of character vectors. ls is a command that basically gives you everything in the environment. So here, if you do ls and parentheses, you basically get df and enhance, which are the two objects contained in your environment. So ls gives you all objects in your environment. RM list equals ls deletes everything in the environment. Now it's all done. Good. Hi, Sarah. So now essentially when you start dfm2, is this being the codes that you use to compute this table. You basically see now, I'm just stopping this here. You basically see the table shown in the format that essentially is used in your so this was essentially the table that we built in Excel. That was our congruent incongruent example. We have here the IDs of 24 participants. We have the congruent Stroop example participants, and we have the incongruent Stroop sample or Stroop test results. If we want to just, so this is a data frame, essentially builds you a data frame based on whatever you are asking R to build. So if I just would do data frame and then the variable defined as ID, I basically can with C, give it a list of vectors. So if I just look at C, 1, 2, 3, 4, 5, 24, that essentially is just a vector from 1 to 24. So if I say data frame ID C from 1 to 24, essentially that just gives me a list from 1 to 24 labeled as a variable ID. So if so now everything needs to be separated by parentheses. With a comma, you basically indicate after this parentheses that there's a second variable coming, which is here congruent. And again, the same principle applies here. So congruent, this C is essentially nothing else but building a vector. And you just align these vectors with the ID vector. And by that, essentially, you end up getting this dfm2, which is our df for module 2. Essentially then leading to the building of this data frame, which is basically 1 to 24 with congruent and incongruent data entries. if you want to address only one variable in the data frame, so you know now, and list is not only giving you every environmental object. So if you have ls parentheses, you get dfm2, which is one object and the only object right now in the environment. If you do ls dfm2, you get all sub-objects in your main object. So this essentially is here congruent, ID, and incongruent. So you can address each of these sub-objects with giving it the data frame name, which is dfm2, separated by $, gets you congruent. So now it only gives you this variable congruent. The variable congruent at this point is nothing else but a vector. In its presentation here, if I address it just as a sub-object. So essentially then it just gives you a list of numbers that are contained in dfm2 congruent. So it's basically object, sub-object, and that you can address as a vector. So if I want to pack this now in a vector, I just say dfm2 congruent will now be a vector that essentially is now contained in this vector. So if I start vector now, you get basically, you get vector. This is not a list of data entries, right? This is basically consistent with the variable congruent. So if you want to count the length of this vector, you use length, and length essentially makes a count of these entries. This can be done for incongruent and congruent, and with dim, D-I-M, you get the dimensions of the data frame. So this is obviously different than length of the variable because that gives you the length of that vector of the variable per se, whereas dim gets you the dimensions of the entire data frame. So this is 24 entrants, 20 and 24 rows in the data frame with 3 variables. So this basically does address all these entries. So count as per criteria allows to essentially specify the respective entries. So if you have dfm2 congruent, which if we run this, we only get a vector, right? If I run this and I specify now everything that follows this entry, and you know this from data camp, everything that follows the variable, and you specify in the variable what criterion you want to employ on subsetting your variable, will essentially be done with a bracket here. So this in the bracket is essentially a true-false statement. So if you just run dfm2 congruent greater than 15, gives you here 24 entries where you have this is false, this is smaller than 15. This is true because this is greater than 15. This is false, this is smaller than 15. This is false, smaller, false, smaller, false, 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 true. Here, this is larger than 15. No, this is larger than 15. So you need to basically align this, right? So it gives you that list and it tells you which in this list have been true or false. And when you subset it, it will only subset it for the true ones. So it only gives you those that are greater than 15. Same with the incongruence. So here it's longer. So if you do now the same command and use again this length, this is 24, and now you do length on the criterion, you only get 9. So by this, you can easily already count according to criterion. That makes your frequency table exercise quite easy, right? And if you soft code your threshold now, you basically assign threshold to 15, and you're running the same code again, you basically get again the same threshold, but now the threshold is soft coded. So as said, like in a real data analysis in the real world, you would want to define such thresholds at the very beginning of your code, because if you have 3,000 lines of code, you want to know where you defined these thresholds, because if you need to change it like 20 times over 3,000 lines of code, this is super confusing, right? If you do it once in the beginning, you have this variable, your entire length of your script. So if you are running these codes now, it essentially will base it on threshold. If I change the threshold to 12, I have now threshold of 12. You get now 18 and 24. You can increase it. You can, for example, you can increase it to 19. Then essentially your threshold results in a much shorter vector for incongruence exceeding that threshold. So this is essentially what you would be doing for counting according to this. When you want to calculate now means or standard deviations, you can basically do this with mean, defining it as per the threshold. So if you have now, so mean congruent would essentially be a mean of 14. And as you remember from the average calculations, as soon as you use a subset that is higher, and you basically are subsetting it now to only those that do have interest greater than the threshold, your mean also increases. Arithmetically has to increase, right? The same when you compare it to the mean of incongruent. Incongruent is always larger than congruent, which we remember from the Stroop test. This is where the font color and the word written, the color written as a word does not match, then it always takes longer. If you want to compare these two means, you just build the difference, for example, and you get a difference of 7.96 seconds. That's your difference. So you can just easily calculate a mean, subtract that mean from the other variable, from that one. Okay, so this was counting in the Stroop testing. That was simple, right? So now we have DFM3. DFM3 is now that volcano example. And we want to calculate now, or we want to count the number of countries with a certain specific number of volcanoes contained on their soil. So we're building first a data frame that counts from 1 to 17 and creates a frequency column, a frequency variable, which we set to NA. NA is basically an empty cell for R. So whenever there's missing data, R will label this missing cell as NA. So you have now a frequency table that has 17 observations, which is 1 volcano, 2 volcanoes, 3 volcanoes, the number of volcanoes up to 17, just like we did in class, with the frequency all being NA. And now we want to populate this, which we could essentially do easily. And now we look at this volcano data. So we have the volcano country, the volcano housing country, and we have the count of volcanoes on its soil. So if we want to know now which country, and let's just take this snippet, we take length. So we have now length, DFM3 countries. So we're counting the countries where the count of volcanoes equals a number, so 1, okay? So we're setting this to 1, missing bracket. So now this is 14. So just as an example to illustrate this, we're gonna add this code. So we have length DFM3 country with DFM3 count, which is that variable that specifies how many volcanoes are in the country. We're doing this with 1, we're getting 14 as the number. So this is the number of countries that have 1 volcano on its soil. So now I have a repetition. So a for loop is essentially, a for loop means that it will repeat by using this counter I, and it will run this counter I from 1 to 17 times. It will run it once, was the number 1, where I equals 1, then I equals 2. So it will run it through 1 to 17 times, so 17 times. And this I will change with each run to first 1, second run 2, third run 3, fourth run 4. So it will basically change from 1 to 17. So now I'm adding, if I do frequency table frequency, right? So this is in the frequency table. This is now frequency. So I can address each of these cells by saying, okay, so frequency table, $ frequency. So this entry here, if I want frequency table 3, frequency 3. So to frequency table, frequency bracket 3, I get the third entry on the variable frequency, which is NA. But let's say we want to, and this is again where we're using the pipe. We're saying this is now, let's say this is now hello. This is the character. So we're saying now this is hello. You can assign hello to the third entry. You see? So here's the third entry. It's now hello. Good. But we want to not play around with hello. We want to say now for I in 17. So this is runs now through 17 times. For 17 times, it basically jumps now from 1 to 17. So it takes this entry frequency 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It basically takes length. So it counts in the entire list of DFM3 country. It counts the entries that have a count that is consistent with frequency table count I. And frequency table count I is essentially this first column. So it grabs now with every time from 1 to 17 it runs through, it grabs the actual number in this count and uses this as the criterion in the counting. And by that, you essentially are filling all your frequencies. Play around with this part. Once you submitted the practice lab, play around with this part because you can do a lot of great things with it. The for loop is a very useful way of repeating a process that is redundant, does the same thing, but just needs a little bit of a twist to essentially be adapted to your need, and to essentially change something that will allow for you to run a different criteria. So this is what this part means. So now you have essentially your frequency table completed. So this is the volcano example. So now we have, lastly, we have DFM4. We have here a data frame where you have ID, erratic performance, and hours. So now we open this file. We have here an ID. So these are 21 athletes. We have their athletic performance, and we have the hours they put into their practice. So now how did they do? As we always know, what we want to do first is descriptive statistics. And what could be nicer with descriptive statistics? We can build histograms, right? And histograms is used, uses the function hist, H-I-S-T. So hist, DFM4 for athletic performance shows now a histogram of these performances. So now this is the histogram, showing the histogram of the performances. So this is how all the individuals, all the athletes performed. So now if we do hist DFM4 hours, we see now the distribution of how many hours these athletes put into their work. So this is the histogram of hours. Now we remember, like we can individualize the bins, but we're not doing that now. This is too much for now. But another nice way of looking at data, particularly when it comes to these associations, is to use a plot variable. So in the plot variable, we essentially see DFM4 hours DFM4AP. So the first entry is always X. Second entry, or we can also specify, we can say X equals hours and Y equals DFAP. So now we have the same, just because a little bit more clearly defined. XLab gives you the label on the x-axis, YLab gives you the label on the y-axis. So essentially, you have now your scalar plot depicted. And now the next question will be, how can I do a fit line? So the fit line can be done with something that is called airline, and this becomes a little bit more complicated. You need a linear model. So you remember when we talked about fitting a fit line through that scalar, uses an approach named least square fitting or least square regression. So that means that this fit line follows a linear model approach. And that linear model is defined as athletic performance on the y-axis as a function of, and this is indicated by a tilde in this command, by DFM4 hours. So this basically fits that line through. We can change the line type and make this dashed at ty equals 2. So now it's a little bit of a messy one. Now it's a dashed line. So this is how you would reproduce what Excel does with the trend line. This is how you would do that in R. So now the beauty of this is obviously that if we have a change now, this change can be changed quickly. So let's say we have now DFM4 $sign hours. There was a data entry and this hours were now 4,000 rather than its actual entry. So we're changing now this one entry on number 2. So this is the second entry. So the second entry in DFM4 was here 2027. We are overriding this now and we're overriding it as 4,000. So now let's look at the plot. You saw how that changed? And now basically the fit line looks different. And you can reproduce this, whatever you have done, with just simply doing this within a second. Okay. But we want to have the real results, so we're gonna reproduce now DFM4 and we can reproduce the initial data set. And now we're putting it back. Now it's the same as it was before. And this is the beauty of R, where you can go back and you can backpedal from your changes. And you can try things out and you can do things differently and nothing gets lost from the original analysis. So if we do DFM5 now, we essentially see now the entries for the Charity Navigator score. So DFM5 for the Charity Navigator scores, 40 entries for 40 different charities, with one being extremely low. Another very low one is actually not here, but only one reached the 100. So you can also in this data frame, you can sort by just clicking on the variable name. It's a little easier than Excel. We need a function for that. If you do a histogram now, like we did in class, because you get this histogram in a second. Basically, this is the histogram. This is the histogram of your scores. Now I can do a summary of those scores. We're basically building here. You get a whole spread. You get min and max, which basically is the range. You get first and the third quartile, which is the IQR. So if you want to calculate the IQR, you can just simply calculate the difference here, which is 6.3, right? So it's 94.2 minus 87.9 is 6.3. This is numeric summary entry 5. And again, everything becomes an object as soon as you can address it in some way. So this is summary DFM5 score 5 is 1, 2, 3, 4, 5. This is the fifth entry on your summary. So you have here quantile 25% is 87.9. This is the first quartile. But this is another way how you can approach it. You can use quantile, the quantile function. gives you here the third quartile. Summary and summary gives you the same, and I can calculate the difference. So I hope this was a little helpful. It was half an hour. So since there were no specific questions posted to the discussion board, I'm going to leave it at that. I hope this made it a little clearer why I think this practice lab is useful, why this code could be useful. Again, I recommend you save this code somewhere. It could become helpful at one point. Maybe also my explanations here, but also take advantage of the data camp, and I'll see you in class. All right. Bye-bye.